All right, so here we're going to take a look at what's called a conditional probability. A famous problem here in conditional probability is this the Monty Hall problem, right? I think Monty Hall is game show really old, where the idea here is that there are three doors, right? As you see in front of you here, right? It's a simulation here. All right, so the idea is you pick a door. So here, let's say, all right, I'll pick a door here. All right, so this came from a game show, right? So you pick a door, say, pick this one. All right, and it says, are you sure about that? You can still change your mind. So the idea is that, yes, I'm sure. And the idea is that the host will show you one of the other doors, and clearly the one that does is not the winning door, right? So the idea here is that behind these three doors, two of them contain goats, and one of them contains a brand new car. If you select the car, right, you win the car, right? Straightforward. So the problem here is, okay, so he showed you one of the doors that has a goat. And now the next question is, you're given an option. Should you switch your choice? Right? I've chosen here the one on the left. Should I pick the one on the right? Does it matter? Right? Would be a question here, right? Then it doesn't matter. You might think most people say, oh, it's 50-50. Right? Now this is at its root a conditional probability type problem. Right? Now when you first picked that door, whichever one it was, you had a third of a chance to win. Right? Now what conditional probability is going to tell us that you should always switch your choice. In the long run, that is probabilistically, excuse me, having trouble talking, that is a much better bet in the long run. And you should always do that. Now we're going to gain some intuition as to why this happens. Okay? Now we'll get back to this a little later. Okay, so what we have here is the conditional probability of A of A given B. That's kind of how you read this part here. All right, and what this tells me is that it's the probability of A intersection of B over the probability of B. Right, now when we say given B, that means that I know that B has occurred. Right, so we have information, more pieces of information given to us. Right, it's not just a probability of A. Right, it's the probability of A knowing that B has happened. Right, now the intuition, now again, the proof is outside the scope of this class here, but the intuition behind this here is that if we think of our formula here, probability of A intersection B over probability of B, right, of some sample space F, right, then it comes to the idea of counting over S, right, where S is the sample space, all possible outcomes. Right, and then all outcomes in simply B, and we get almost like the S cancels out, and we're left with, right, the size of A intersection B over the size of B. Right, and the idea here is that, well, we know B has happened, so we restrict ourselves in our sample space to only think about events that are in B, and then from there, B becomes our new sample space, right? And we just look at what events are in A that are also in B. So that's kind of the idea behind this formula here. Now let's take a look at an example here. All right, so let's say we roll 2 dice. Now your friend says at least one die shows a 4. Okay, so you're given a hint, right? So now you adjust your thinking, right? You adjust your sample space, right? So you roll 2, you at least one die shows a 4. So what I want to find out, what is the probability that the sum equals 7 given at least one 4? All right. All right, so if we go back to our formula here, probability A given B, right, is equal to the probability of A intersection B over the probability of B. Okay. All right. Okay, so here we have that the size of B, we have 11 pairs containing 4. Okay, now the probability of A intersection B is 2 pairs. Excuse me, sorry. 2 pairs. 3, 4, and 4, 3. All right, so now going back to the probability that the sum is equal to 7, given at least one 4. Is equal to 2 out of 11. All right, now notice here that this changes if I didn't know that at least one of them was 4. All right, if I just was looking for the probability sum is equal to 7 without any other information, that would be 6 out of 36, right? So there are 36 possible rows of 2 6-sided die, right? Remember, 6 outcome product principle, 6 outcomes each die, so 6 times 6 is 36. And we see knowing more information has increased our chances, right? It has changed the probability, in other words. Okay? All right. Now another example here. Think of cards. So we draw 2 cards in order. And then A, the first card is red. And B, second card is a face card. Okay, so let's say here the probability of B given A Okay, so here we have that the probability that the second card is a face card given that the first card is red. Okay. So remember, each suit, there are 3 face cards, right? The king, the queen, and the jack. All right, now if we switch this around, this gives me probability of A, right? Probability of B intersection with A. All right, so if I know the first card is red, so that's half the deck, right? So A is 26. Okay. Excuse me. And then probability of B intersected with A, right? Of those 26 red cards, 3 hearts, 3 diamonds are face cards, so we have 6. Okay, so this would be here 6 over 26, or 3/13. All right, so again, notice this changes the probability. If I just was looking for a face card, right, that would be a much different probability here. Now, on the flip side, now this one's interesting here, probability of A given B. All right. So if we look at this, right, so I know that the second card is a face card, right, so this would be here, but again, A is the first card here. The first card is red, right? So something like this, we notice that what the second card is really doesn't matter. It doesn't affect what the probability of A is going to be, right? This is going to be equivalent to the probability of A. Okay, so here if we look at the calculation here, right? B intersection of A. Right, that is 6. Excuse me, using the formula here. And B was, second card is a face card here. So here, the sample space here for B is, so 4 suits, 3 face cards, that would be 12. All right, so we get 6 over 12, which is 1/2. All right, and again, that's equivalent to the probability of A, right, that the first one is red. All right, given that the second card is a face card, right, if it's red, well, that's half the deck, right, so it makes sense that it's a half as well. All right, now when this happens here, like, this is the idea of an independent event, right? So another definition we saw previously, we defined what independent event means. Well, in this case like this, it's independent, then A given B is the same as the probability of A. That you gain no knowledge on A if you know that B occurred, right? That's kind of what's going on here, right? And again here, from the formula here, probability of A given B, probability of A intersection B, right? But if A and B are independent, we saw that that's the same as the product principle for probability, right? And these reduce, so we get the probability of A. All right. So essentially, right, knowing B occurred doesn't give me any additional information on A. All right. Now, back to this Monty Hall problem before we end this video here. Okay, so here, all right, running through the simulation here, it states, all right, are we sure? Right. So here, great choice, but let me make life a little easier, I'll open one of the other doors with a goat so that there's only 2 doors left. So again here, given the option, I want to stay, I want to swap. So I will swap. All right, open the doors and we see that success. I won the car, right? Now, here, we could replay the game, but again, right, we get the idea here. You'll notice that you're more likely to win if you swap after the first door is open, but rather than sticking with your initial choice. But why is that the case? Right? When you pick the initial door, the probability of being correct is 1/3. Right? You're correct 33% of the time. All right? After the game master opens the door, right, the probability of being wrong is still 2/3. Except now all that probability is just on one door. So what that means is that swapping the doors doubles your chances of winning, right? Even if this may not seem intuitive at all to you, right? I think here, I remember this problem was something that we talked about extensively in my probability course as an undergrad, right? And it's just kind of hard to wrap your head around to think that you go from 1/3 to 2/3 probability of winning. Now here is, we can lay out all the different probabilities here. Right, so here, if you look at these 3 columns, it is broken down into, well, if the car is in the first door, then there are 3 choices, right? You either choose the first door, choose the second door, choose the third door. Okay? Then if the car is in the second door, then you can either choose the first door, second door, third door, etc. Okay? Now there are 9 possibilities, right, of the choices you can make depending on where the car is. Now if you think here, so if you choose the one with the goat, there are 6 where you need to switch the doors in order to win, right? This gives a chance of 6 out of 9, which is 2/3, right? Which is much different than 1/3 in the original start of the game where you had no new information. Okay, so again, right, very subtle here, but again, given a choice here where some new information is revealed, in this case the goat behind the door, always switch your choice.